Hello everybody, thank you for joining us at the presentation on the fault and fracture network analysis and modeling in this challenging, complex geological environment of the Palaeozoic tide reservoirs in Algeria. I hope you will enjoy it. So here we see the general workflow for the modeling of faulted and fractured reservoirs. On the right side we see the dynamic description and the well test history matching. On the left side we see the static description and the construction of a conceptual geological model for the reservoir, which will be the argument of this present paper. One of the main characteristics of fault and fracture networks is that they appear on various scales, represented in this diagram. From left to right we go from bigger to smaller scale. We see observation area becoming smaller, resolution becoming bigger, average lengths of the features observed become smaller, and the density of course become higher. If we go on the left we see the seismic data, on the right we see image log and core data and thin section data, and the smaller scale. In the intermediate scale can be filled in with outcrop and satellite data. The same way we see highly persistent fractures and faults on the larger intermediate scales, and joints and microfractures on the smaller scale, which can be observed in a continuous way if we combine the data sets from larger to smaller scales, as we will see in this presentation. This diagram describes the relationship between the different features observed over the different scale ranges in terms of length, plotted on the horizontal axis, and size or aperture, plotted on the vertical axis. Amount of features observed rapidly decreases, whereas aperture of the features rapidly increases. If we look at the data presented in literature, we see that on the small scale, the veins correlate with dikes, showing mode 1 opening, whereas single and multiple segment veins correlate with faults, showing mode 2 and mode 3 displacements. In mathematical terms, this can be expressed in power law, fractal, or more in general, exponential functions. So in this diagram we anticipate the result of the analysis, the multiscale analysis of over 10,000 fractures in this area. We see the relationship between the length on the horizontal axis and the number of fractures on the vertical axis in a negative cumulative way. We can see that basically they plot along a general straight line, but there are specific deviations from this line for certain groups of data, and we'll come back to this later. General setting of the study area in central Algeria. In the west, the Ahnet Basin. In the east, the main area of study of the Ghadames-Berkine Basin, Illizi Basin, and Tassili outcrop area. A well-known map of the subcrop of the Palaeozoic below the Hercynian unconformity in North Africa. In the east, the Berkine-Ghadames Basin, subject of study, and south of this, the Tassili outcrop area, and the section in the next slide which illustrates this geological situation. North-south cross-section through the area of study. From the north, the Berkine-Ghadames Basin, to the south through the Illizi Basin to the Tassili outcrops. Targets reservoirs of Paleozoic times. Clearly distinguished is the Hercynian unconformity separating the deformed Paleozoic sequences from the Mesozoic series, and the Tassili outcrop as analog for the subsurface reservoirs. The Paleozoic stratigraphy of the area, we can clearly distinguish the Ordovician sequences with channels related to glacial environments, the Silurian hot shales and the Silurian reservoirs, indicated the area of study, and how these different sequences are expressed in the well logs. A diagram of the subdivision of the Ordovician reservoir in layers based on the recognition of different phases, with on the right side a correlation with the seismic expression, and on the left side how they are expressed in a type well log. In this example of a CPI diagram, we see the challenges we are facing. We have low porosity and permeability from cores. We have pay zones shown clearly from the petrophysical analysis, and these zones flow in open hole DST well tests more than we should expect from only matrix porosity. So we ask ourselves, what is the contribution of the fracture zones and the fracture corridors, and what is the actual impact of primary porosity permeability variations due to phases. Let's take a look at the evolution of the faulting and the fracturing. First, the deposition of the Palaeozoic sequences, compaction and fracturing, and the development of a well-defined regional joint pattern. Basin deepening to the north, and the development during Hercynian deformation of a clearly defined sinistral shear fault pattern. Regional tilting to the north, burial, maturation, the development of the Mesozoic basin, and during later stage, and especially present day, the application of a regional stress field upon all the previously developed structures. To anticipate the structural model for the fault and the fracture systems, we distinguish a joint pattern on the smaller scale from a fault pattern on the larger scale, well-defined 3 sets of joints and well-defined sets of faults, part of which are reactivations of the previously developed joint sets. An example of Hercynian anticlines outcropping in the eastern part of the area, well defined on the satellite photography, and they can be mapped in great detail and correlated to the structures as visible in the seismic. So one of the main arguments of this presentation is the possibility to connect the subsurface structures to outcropping analogues in the south in the Tassili area. So let's take a look at some examples. Here we see an image representing the top of the Ordovician reservoir and the contact with the overlying Silurian section, which starts with the hot shales, which also constitutes the seal of the reservoir. Then here we see the top of the Ordovician reservoir with well recognizable channel systems, which can be mapped using the satellite images. And here we see an example of the outcrop of the Ordovician series with well-defined fault and fracture zones. And here we can see on the satellite images fault and fracture zones cross-cutting the Ordovician series. A fundamental aspect that has to be taken into account in the analysis of fractured and faulted reservoirs is the characterization of the present-day regional stress field. Here the importance of the use of the regional stress field for recognition of the anisotropy of depletion, directional drilling, fracture simulation design, and how it can be recognized in this case using especially the borehole image logs and earthquake focal mechanisms. In our case, we are dealing with north-northwest, south-southeast oriented compressive maximum horizontal stress, which is confirmed by all the data from the image logs. So let's take a look at the data available on microfractures and joints and fractures in the small-scale domain. In this well correlation panel, we can see that the reservoir units are consistent and can be traced over large distances. So here a porosity permeability cross plot for the top Ordovician unit, and we can clearly see low permeabilities, wide ranges in porosities, and we can distinguish two different phases. Here a porosity permeability cross plot for the central part of the Ordovician reservoir unit, and we can see high ranges in porosities, still low permeabilities, and a few high permeabilities on sedimentological features and fractures. Here the different discontinuities that can be observed on the core, subhorizontal bedding, open joints, hairline fractures. Some results of the numerical analysis on the discontinuities, the fracture spacing, fracture sizes, and some information on the fracture orientation. Next, we take a look at the data from the image logs. Few image logs are available, but most of the logs show fractures present along fracture corridors with densely spaced fractures. Next, the available information on the larger scale from the subsurface on the 3D seismic. Here an example of the recognition of the fracture corridors and fracture zones on the seismic and the projection on the top of the reservoir. Well, these fracture zones can clearly be mapped in the seismic, and we can distinguish the sets and analyze the statistics of the length-density relationships and the orientation. Next, the data available that fill the gap in the subsurface between the image log core data on the smaller scale and the seismic data on the larger scale. On this slide, the correlation between, in the north, the subsurface situation, and in the south, the outcropping series, which have been analyzed on satellite photography. In the green box, the Cambro Ordovician series, on which different pavements of different scales have been analyzed and measured. So let's go through a few examples from the larger to the smaller scale. Here we see the kilometer scale, which is comparable to seismics, in which clearly fault zones can be recognized. We go to the hundreds of meter scale, in which fracture corridors can be recognized. Go to the tens of meter scale, larger joint sets, and to the meter scale, in which we see clearly defined joint sets. Of course, the large scale is related to the fault pattern, and the smaller scale related to the joint patterns. And here we see the result of these analyses on the different scales. On the left we see the smaller scale, in which we clearly can define the series of joint sets, and on the right side we see the larger scale, in which we can clearly define the different fault related sets. And we can see that some of the fault sets are reactivation of well-defined joint sets, and we can make a correlation between the different scales and the different observations. If we plot all the data observed on the different scales in one and the same diagram, length versus the number of fractures observed, we see some sort of a positive correlation, but we can also see quite some variation. Here then a completely new feature, which is the mathematical distinction between the larger and the smaller scale. We see this in three different diagrams. Let's focus on the left one. We see the clear correlation between the microfractures and the core data and the joints that have been observed in the remote sensing outcrop data. And on the larger scale, a different mathematical property for the fault and the fracture corridors. This brings us to the construction of a well-scale geological conceptual model. Here we see a 1 meter scale model, how it is manifested in section view on core data and log data, and top view in the outcrops. Hydrocarbons, of course, we imagine they move from the matrix to the joints. Therefore, in the dual porosity, dual permeability model, we imagine a matrix porosity and a very low permeability, and the joint system with a certain fracture porosity, very low, and a fracture permeability. Now, what we imagine, of course, is the matrix porosity between 1.5 and 8%. It constitutes the volume of the reservoir. On the other side, the fracture permeability constitutes the transmissivity for the reservoir. And together they are the effective properties of the reservoir. Now, this is the reservoir block scale conceptual model. Centered around the well and built upon the reservoir layers we have identified. It is a 700 meter scale model, more or less, and here we see the frac job result that would stimulate the joint network and the larger highly persistent fractures transecting the reservoir. Of course, we have to imagine the scale difference between what is the core scale, small scale model with the small scale joint, which transfer the hydrocarbons to the larger scale joint network. Important to understand that the fracture density is of course quite low for the larger scale fractures, but the amount of highly persistent fractures that transect the different reservoir layers. In this sort of model, we should expect around 600 to be present. Permits basically that the different reservoirs layers can communicate between each other in a vertical scale. Here one extra dimension added to the model, which is a subseismic scale 3D discrete fault and fracture model generated by the FPDM module FD5D. It is based on the seismic attributes that have been extracted and generated by an artificially intelligent algorithm. And we come to a few conclusions. Confirmed is, of course, that mathematical methods permit to connect the data from the different sources over the multiple scale ranges. And we see promising new technologies that permits to fill the gaps over the different scale ranges. A new feature is that the distributions of the fracture and the fault properties, they show distinct, newly discovered mathematical definitions, different for the different scale ranges. We have a capability to model complex 3D connectivity and anisotropy that can be characterized and represented in DFN and models, the DMX protocol. Of course, we have an aspiration to use all these models in future planning of exploration, appraisal and development wells. Planning, we have to recognize that in a fracking program it is important to obtain commercial flow rates, and different strategies could be confronted, like open hole, fracking and directional. And there are a few recommendations. Multi-component azimuthal 3D seismic inversion technologies, horizontal wells should target the subsurface fracture and fault zones that can be modeled, well testing and fracking designs, maybe open hole, seismicity monitoring during the fracking, and promising deep shear wave imaging technologies. Well, thank you for your attention, and my gratitude goes to EAGE for the possibility to present this paper, and hope to see you next time.